Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, let's get started. So in Dan's keynote, he mentioned a couple of things that's related to this session. Citizen science, and also one of the examples in that environmental informatics framework that he showed. And Jung is going to start with our first presentation in this session about a citizen science using Windows mobile device. So Jung.
All right. Well, good morning. Sound is okay? Okay. My name is Yong Liu. I'm from National Center for Supercomputing Applications at the University of Illinois, Urbana-Champaign. So today it's my pleasure to present our work in using Windows Phone 7 for some citizen science experiment we have done in the past year. So here's my presentation outline. First, I'll talk about the motivation and background of this work. And primarily, the application area I'm interested in is in emergency management. So the second part, I will talk about the issues and the challenges related to citizen science practice in general, but also emergency management in particular. And then I will outline our research objectives, requirement analysis, and then our design. And then I'll present some of the details of our implementation and experiment we have done. In particular, I'll talk about the Mapster, a prototype that we developed for new citizen science practice, and video demo. And then some of the ongoing and future work will be briefly mentioned, and then finally a summary and conclusion. So first is about the motivation and some of the background information, why we are interested in citizen science, and what's the relationship between all the things that we have done in environment area related to mobile computing or social media even. So in the past few years, there's a very visible trend, a grassroots movement almost, by using social media, and in particular Twitter, to help disaster relief effort, to enhance all kinds of the emergency management practice. So for example, most recent one is actually in Thailand. In the past few months, there's a surge usage of social media, and in particular Twitter. So I've got some statistic actually right from the website. So in the past 2 months, basically that's September and October, Twitter has enjoyed a 20% spike in user numbers in Thailand in the past 2 months. And the hashtag Thai flood has notched up more than 500,000 hits in October 2011. So that's a huge number of information exchange and updates about the flooding situation in Thailand. And of course, previously in Haiti, actually there's a massive usage of Twitter for disaster relief. So those are all unorganized citizen effort, actually. From the other side, like from top down, there's actually also a emergency management authority or a government agency. They are also realizing all these related efforts. So recently released a report from National Weather Service in the US about the tornado event in Joplin, Missouri, in May 2011, actually made several recommendations for future relief efforts. One of them, key recommendation, is to develop GPS-based warning communications, including the use of text messaging, smartphone apps, mobile communication technologies. So there's basically from the government agency, from the citizen perspective, there's a strong need to actually help improve both the disaster relief effort itself as well as the citizen involvement. So as we all know, any improvement in helping emergency management will reduce property damage, maybe also reduce the number of human deaths as well. So it is very critical. So for example, this is a chart produced by NOAA in the US, basically describing the historical US floods loss damage in the past 20 years. So on average, in the last 20 years, the average loss due to flooding is about $8 billion per year, US dollar. And in recent years, you can see the trend actually is increasing. So like in 2005, the loss due to flooding is almost 50 billion US dollars. So because of the climate change and urbanization and all kinds of things that we know, this can only increase in the foreseeable future. So I'll talk about the current issues and challenges of current citizen science practice, actually, in particular related to all these kind of flooding, emergency management things. So citizens have always been involved with many science projects or citizen science projects and emergency management, but limitations exist. So here we list the three major limitations that we would like to address in our project. So first is limited one-way citizen participation. By that I mean that citizens usually do participate, but they just maybe send some information or call some authority, and then they provide information, but they never get immediate feedback either from the agency or from their peers. So for example, this is just an ecology citizen science project called the Lost Ladybug project. So people basically observe or take pictures in their backyard of some ladybug, and then they send the picture to the website, and that's it. They don't get near real-time response at all. Of course, this is not an emergency situation, but this is actually very common in many citizen science projects, including emergency management practice. And then the second is there's a lack of integration of both citizen reports, observation, and infrastructure sensing. So by that, I mean basically people can post or share their individual observation, but there's no integration of their data with like government agency provided infrastructure-based sensing data. So for example, there's a very well-known citizen science project called COCO-RAS in the US, which basically is now available in all 50 states in the United States. So what they do is basically ask residents, citizens, to install rain gauge in their backyard and then report their rain gauge reading every day and to this website. So this is very helpful, but USGS and other local government agencies also maintain rain gauge and other radar instruments. There is no integration of this data with the radar and other government-provided data. So there is no verification and other things that you can do. And thirdly, there is a lack of location-based personalized spatial temporal visualization animation tool. This is particularly significant when you're actually dealing with emergency situation, because you don't want to just ask people to send the information and then that's it. You want that, give them feedback about what they are currently experienced with. So what we need is support for real-time personalized situation awareness, not just ask people to provide information, but actually give back some additional value-added information. So having identified those limitations, our research objectives are basically threefold. First, we want to investigate and develop some a new real-time citizen reporting tool on a smartphone. And we would like to leverage existing knowledge in emergency management. I will elaborate that in particular in our next few slides. And we'd like to sustain citizens' multi-way participation and then support location-based reporting. Second objective is to do data integration and processing in the cloud so that we can support heterogeneous data fetching, transformation, and republishing as streaming data service. And third, we would like to have an integrated spatial temporal animation of both citizen reports and agency-owned sensor data on a smartphone so that we can improve personalized situational awareness. So I'll go through these objectives one by one and then present corresponding proposed solution that we have. So the first one is investigation and development of a new real-time citizen reporting tool on a smartphone. So traditionally, citizen reporting mechanism is basically in the form of citizen information line. So usually there's a landline phone number you can call during certain event. Citizen basically pick up a phone and report a certain kind of event on a particular location. So for example, one of the major, largest water management district in the US, South Florida Water Management District, they maintain a dedicated landline for citizens to call in. And then also they maintain a separate database for those category information, citizen provided information. So for example, like a basement flooding, power line down, road impassable. So they record all of them, but they put it in a separate database and then they will actually get used to get integrated with other things. So we think that we need to formalize and use the new citizen reporting mechanism, which is Twitter plus smartphone. The reasons are very obvious. So the first reason is that there are already a large number of citizens using these tools. So for example, as of July 2011, there are over 200 million users on Twitter and 350 billion tweets are posted per day. And these numbers are only going up. For the smartphone owner, as of August 2011, there are over 85 million people in the US actually have a smartphone or maybe multiple smartphones. So the presence and where the users are very important. So those are the important information. And then secondly, we think by using this new kind of citizen reporting mechanism, we will have effective citizen engagement and long-term sustainability of any citizen science project. Because there is a very low entry barrier to join. If you have a Twitter account, if you have a smartphone, you can join as long as we actually set up the right tool. So that's why we need to develop our tools based on this new mechanism. And there's also a social network effect because you can actually help each other through the social network side. And then also location-based information collection and reporting is basically an easy feature that you can incorporate. So our design consideration of customized real-time reporting tool on smartphone the following. So first, we want to leverage existing controlled vocabularies. By that, we mean those events that have been previously reported and categorized by the emergency management authority should be reused. So for example, basement flooding, power line die. Those are the events and the controlled vocabularies people are already used. And we want to reuse or leverage that. And a customized Twitter application on a smartphone should allow use of Twitter account to log into the reporting tool. And we should enable automatic generation of hashtags that are corresponding to those previously known event categories. And then, of course, GPS coordinates should be automatically attached to the tweet. And then lastly, but also very important, is that we can reuse the security and the privacy policy from Twitter, because when people actually using those Twitter accounts, they all agree with the policy that the Twitter actually already imposed. So we don't need to reinvent that sort of new protocols and new platforms just for a particular citizen science project. So that's the first one. The second objective is to do data integration and processing in the cloud so that we can support heterogeneous data fetching, transformation, and the republishing of the data streams that we are interested in. So in particular, we would like to have real-time Twitter data fetcher. And this is not just a simple reuse of Twitter streaming API, because Twitter already provides a Twitter streaming API that you can program against. It's a push-based data collection in real time, so you can get real-time tweets. But we actually enhance it with semantic streaming data modeling and storage in the cloud so that we can actually model each tweet or the tweet posts as geo-referenced time series data so that we can actually improve the interoperability of Twitter feeds with other geo-referenced data streams, so such as rainfall time series and other radar data or other commonly seen environment time series data. And then thirdly, we want location-based data fetching, because you don't need to fetch all the data in the whole wide world, because you are mostly all those emergency or disaster are location-based. So you want, for example, only fetch all events within a 20-mile radius of a user's current location. So once you have collect all those data, you want to actually provide value-added web service of all those data as something that the other application, and in particular, in our case, the later on the spatial temporal visualization tool can actually use them. So we would like to provide a geo-referenced streaming RESTful service, which of course can provide latitude, longitude for each streaming, not just the whole streaming time series, but for each particular frame, we can provide geolocation information. And we can also provide time-annotated KML and other formats that people might want to use. And we also use standard ontologies for geolocation. WGS84 is the one that we use. And we would like to support the emerging OGC, that's the Open Geospatial Consortium, GeoSparkle standardized vocabularies, where we can actually provide more geospatial capabilities and query capabilities. And finally, the REST endpoints we provide should enable access to both the metadata for the stream and the frame as well. So that's for the data processing in the cloud part. And then the third objective is that to have an integrated smartphone-based spatial temporal animation of both citizen-provided tweets and agency-owned sensor data on a smartphone. So the example I would like to give to illustrate this is that one would like to visualize both the basement flooding Twitter reports and the U.S. National Weather Service radar data in the last 10 hours within the radius of 10 miles of the phone, so that you can actually have a visual understanding of how the storm is progressing and how the citizen actually responding or reporting those events. So the design consideration of localized spatial temporal animation tool on phone to allow consuming both Open Geospatial Consortium's web mapping service time series sensor data and the GeoStreaming service I just talked about in the second objective, the GeoStreaming data service. And then we also allow to have animation of multiple data types in space and time on a map-based interface on the phone. So based on our analysis requirements and the design, we have an implementation and have done some preliminary experiments. The platform we choose for the phone is the Windows Phone 7. And for the cloud, we basically use, we can use any virtual machine, actually any cloud. But we also test and implement on Azure to host the streaming data processing. And here also I highlight several software service we use, including BeamMap, OGC Web Mapping Service, because this is a standard. So once we support this, we can support the multiple data source we are interested in, Twitter Streaming API, Yahoo Geocoding API service. And that's basically for translating between GPS coordinates and the street address. And we have done some preliminary experiment on the campus of University of Illinois. So in the following slides, I'll just show the architecture of our system, some of the features. And the system we implemented is called Mapster. So as you can see, we can use a Windows Phone to report events into Twitter, and then our streaming data service can fetch it and then processing and provide our streaming data RESTful API, and then we can consume any web mapping service time series data. In this particular case, this picture basically shows the radar data, the National Weather Service data, and you can actually visualize them on your phone. So here is just some of the feature highlights you can capture from the phone. So you can actually look at the weather, you can report events. This is the report event user interface. You can look at the Twitter in the last 10 hours. You can overlay radar map, and you look at the details of each tweet. And you can do spatial temporal animation of both the radar events as well as the tweet. And I actually have a video to see how Mapster is in action, but the YouTube post actually is rather low quality, so I just show you the MP4 video. So this is just our project website. Okay, so having actually implement this prototype, we are looking for possible future citizen science test bed. Or one of the discussions on the way right now is a collaboration with Professor David Maidman at the University of Texas at Austin. Texas has experienced both severe flood and drought in the last 2 years. That's 2010 and 2011. So in 2010, there was a big storm called Storm Hermine. So they have experienced several human deaths and huge property loss. But this year, 2011, Texas has experienced a severe drought they haven't seen for a long time. So if you look at the map here, all these dark brown areas are the category 4 drought, exceptionally dry condition they have experienced. And this is the latest map, actually. And so both flooding and drought are basically the major events they have. And I think they have already have a very good prediction forecasting that next year will be another drought year. But in any case, this is we think this is something that we possibly can actually deploy this kind of citizen science tools and allow citizens to report and just participate in a new citizens kind of a citizen science practice. So several ongoing and future research directions. So we already actually have done some integration of non-Twitter-based reports based on some feedback and experience. So something like a Facebook post or public safety feeds from police, etc. And we are also interested in integration of other virtual sensor streams. By virtual sensor, we mean data streams that have been processed, transformed by some models, and then you republished immediately as if it's some kind of sensor streams that come from the real world. So, for example, NOAA is actually is in the process of trying to experimentally publish hydrological forecast data for water level in the river, so you can actually see how the water level change in the next, for example, several hours. So we would like to integrate that so that people actually can have those kind of information on their phone. And we would like to further integrate social network into the system by showing friends and families physical presence in the cell phone on the map. We would enable more collaborative disaster relief or collaborative assessment kind of system. And we are interested in quantifying the contribution and trustworthiness of citizen-provided data. There's very little work on this area because in the past, people are mostly pushing towards just collecting data and get it, and that's it. But it's very hard to quantify how much contribution people actually have made. And we think that's basically the next phase of intensive research needed. One of the things we are considering is basically you probably can validate citizen-provided data with co-located infrastructure sensing. So the example I gave at the very beginning, like a cocoa rust, people basically report rainfall measurement in their backyard. So it's possible you can actually correlate that with USGS rain gauge or even interpolated value from National Weather Service radar data. So we already have pieces in all these areas. And we can also actually try to calibrate or error checking with scientific simulation models. So for example, the NOAA hydrological forecast data can be used people actually reporting like water level and other things. And we are also in the process of integrating portable narrow sensors to the cell phone for more quantitative citizen sensing and reports. In the past, I think most of the citizen reports are basically just social media and text-based qualitative observation. But the fast-growing development of narrow sensor actually gave us a very good chance to do this kind of more quantitative citizen science or citizen sensing. And in the campus of University of Illinois, we are actually collaborating a group of researchers from ECE department. They are developing the next generation of nano sensor to measure not only just physical parameters in the environment, but also biochemistry parameters, variables like nitrogen, phosphorus. So those are very unique capability that we can bring into the next generation of citizen sensing and citizen science. So in summary, we have designed and developed a new citizen science framework system called Mapster, which can provide a new citizen reporting tool on a Windows Phone 7. We can provide a cloud-based semantic streaming data fetching, processing, and republishing. And we can provide a personalized, localized spatial temporal visualization and animation tool on Windows Phone 7. And then we think the practice of citizen science can be improved by using Mapster through this multi-way citizen participation, reuse of controlled vocabularies through Twitter posting and annotation, semantically enhanced data stream processing and service, and then integrated the data visualization and animation in space and time for both citizen-reported events and infrastructure sensing. So this is my sort of like a envision a statement that we think that a new era of citizen science has arrived. So finally, this is my acknowledgement slides. We thank Microsoft Research provided funding and support for this work. We have been collaborating with 2 programs in Microsoft Research, Project Hawaii and Environmental Informatics Framework, Earth, Energy, and Environment. And I think our team at NCSA, University of Illinois, provided lots of effort to make this happen. Also, MSR, Arjun Samuel is the program manager for Project Hawaii. Dr. Lianshu is the program manager for the Environmental Informatics Framework. They helped us a lot during this past year. So if you have any question, just let me know. Thank you for your attention.
One person can observe one thing at different angle. Some other person can detect it like in different way. How can I rely on this observation that or whatever animation I am seeing? And
yeah. So your question, the question was, how can I rely on citizen-provided data? Because they may provide data from different perspectives, sometimes maybe in very different ways. So yeah, so that's a good question. Actually, that's something I mentioned in our ongoing future research slide. So I think at this moment, we have several ways to dealing with it. One of the things I mentioned is that you can actually use infrastructure sensing data, like for example, the agency-owned data to validate those reports. But if those reports are mostly qualitative, people basically provide event, like some event happens, like you just report your basement is flooded. There's no way to verify how much, what level is in your basement. But at least that event is actually very useful. So how do we combine those qualitative reports with more quantitative measurement from agency-owned data is current research, actually. So I don't have one answer to that. So you can also try other approach. So for example, you can use a simulation model. Basically, you calibrate your model very good. So if you want to measure, if you want to say, well, some of the reports of basement flooding is unlikely to happen, but there are actually reports from the area. So that you can see some contradictory, but you cannot basically say that's not going to happen because my model just said it's not going to happen. So there's a two-way validation. You need the citizen to provide accurate data, but at the same time, you cannot basically say, because your report is contradictory to my common sense and my model, then I cannot trust it. So, of course, you can also go to another route and say, of course, there's another level of trust, basically, whether the citizen reports are actually accurate or not, right? So if they say, oh, do they actually make false reports? I mean, that's a different thing. So.
Yeah, if I may.
Mm-hmm.
That's actually a very good question.
Mm-hmm.
Citizen science is one. One of the discussions that we had at Citizen Web Enablement recently
Mm-hmm.
is that we discussed perhaps one solution is to apply workflow behind the data. So when the data comes in, automatically fit into through a pipeline of one data process. So from there, I can validate the data. It is actually, in some other citizen science projects, we do face serious challenges with tons of data, and a lot of them are really bad quality. So you can't just tell the participants about that without a solution. So that is actually not only a good question, it's actually a very challenging issue that we're still working on.
My question is actually connected with this,
Mm-hmm.
because I read some news that in the United States, they are changing trial laws, or they are thinking of changing trial procedures, because witnesses are not really reliable.
Mm.
And that has to do with brain processing and whatever. So they are thinking about witnesses as being backup or additional information to what is gotten from, let us say, sensors,
Mm-hmm.
films and cameras and things like that. So would you consider outside information to complement or to validate it? How does this work? How would this work?
Yeah. So the question was if we actually can add external information and the sensor data to quantifying the quality of the citizen report. Yeah, I think that's exactly what we are talking about for the last one. Actually, not this one, actually. Yeah. The last one, integrating portable narrow sensors to the cell phone for more quantitative citizen sensing. So many of the data, especially during emergency situation, you cannot repeat. Once you pass that particular time and location, you cannot recollect those data. So instead of relying on citizens' eyes and their text message, you would maybe attach some kind of the portable narrow sensor to augment your human observation with more quantitative data. And we are actually in the process of actually adding that in our system. So that's definitely a huge advantage. So you are no longer just say, my basement is flooded and or the sewer is broken, and you can also measure the contaminants, the concentration, and other things, and you can actually report that together with your event report.
Several different things, but if you have good sensor data, you don't need citizen scientists. Now, the issue of filtering of that input, I think really is crucial. But then, what do you filter? And there are different kinds of input that citizen scientists can provide. One is essentially quantitative measurement of some kind, like they can report temperature or something like that. So numbers, and we know how to deal with numbers. Or even image of something. But what if you are asking for is their opinion, or rather human pattern recognition skill? You're looking at some messy data or messy situation, and your brain knows exactly, well, this is what's really going on. And so essentially, citizen scientists are providing a description of something, whether it's scene or image, it doesn't matter. How do you convert that kind of an input into something that's actionable by a machine, either as numbers or as semantic quantities? Wouldn't it be better if you say have an interface whereby normal citizens can actually enter things in such a way that is converted by the interface into, say, clean semantic statements that the machine can operate?
Mm-hmm. Yeah, that's a good question. So the way we say reuse or leverage existing knowledge in emergency management situation, because that's the use case I'm mostly focused on, reuse or leverage the control vocabularies is one way to actually categorize human observation and those qualitative description. So once you can automatically annotate those qualitative text reports into some kind of previously known human knowledge, because you, if you survey all the agencies like water management district, you will see there's a very clear pattern what they are looking for when the people actually report. So in the past, all those categorizations are done by human, by the phone operator. They basically say they got a phone call, and then the people on the phone basically describe certain things, and then they say this should be in this category. So that's basement flooding, or that's in power line down, and those kind. They have very concrete categorizations, and we actually when we look at their database. Example from South Florida Water Management District, they have more than 30 categorizations of all the human reports. So how do we actually leverage those known events and previous knowledge and put some kind of semantics understanding in it? I think that's I think we are just starting addressing it in a very preliminary way, although I'm using hashtag and other things. But maybe we can do more sophisticated natural language processing.
Expert in line who's going to interpret what
right.
non-expert is saying. That,
right.
It's kind of wasting
It goes
yeah.
beyond this scope.
Right.
So one of the proposals that Barbara Minsker was trying to do, another researcher at UIUC put together a proposal to, and it's is to study the taxonomy, vocabulary, to address that. Involves psychologists and human
Right.
study. Didn't get funded because it involves so many players. We can take that offline.
Yeah.
This is the next, and then goes to you. Cool question. Yeah.
I was just curious on, so you have like personalized reports that one person could look at on their phone. What about if you're the Southwest Florida water district and there's a storm hitting? What do they see?
They can pick all.
Do they just look at this data? Is it personalized, or do they get a more summarized view, or does it doesn't really matter?
Well, if you are looking at the overall data, of course you can use it in whatever way you want, because the data actually is being processed. The data is being processed in the cloud. So we have the storage, and in the cloud you can actually use it in a very loosely coupled way. So you can get all the data you want. But in terms of the cell phone, you can also check mark whichever data streams you are interested in. So that's the personalized part. If you are just interested in a particular data stream, you just check mark that. Yeah. But you can check all of them. There are many of them available there. Yeah.
To follow on the issue of the ambiguous statements, natural language programming is not so bad, so you could get some idea of what's going on. So one thing to do to take the statements in, process them, come up with a set of options about what may actually be discussed, and send back messages to people in that area, saying, if you're around, well, what have you seen? And then try and work out from that what actually is happening.
Yeah.
Feedback between.
Yeah.
Guided.
Yeah.
Yes. Well, you created guided statements, not just back to the person who sent it to confirm which one of these things is reality. Did you mean
Right.
or none? But to other people in the local area. I mean, if you've got a flooded basement, then presumably you might want to send messages to other phones around saying, is your basement flooded as well? Or is this just a...
Yeah.
Yes.
Yeah. So, okay. So I don't need to
Well,
summarize it.
running out
We are now running out of time. Okay.
So this is great. Let's just continue over the lunch. Now we're switching gears.
Mhm.
People have that information. You can ask questions.
First off, a couple of your examples that you indicate show that citizen science don't work are just examples. And there are many projects in citizen science that do all the things that you said citizen science projects don't do. So I think it's important to be careful not to use anecdotes to make broad statements. The second thing is regarding data quality. During the citizen science session, there'll be, I think, 3 different papers discussing data quality and issues of data quality, using different approaches to do that. And then the third issue is how do you define, or you didn't define what citizen science is. And so you were talking very broadly about everything from reporting an event, which I don't necessarily think of as citizen science, and not talked a lot about structured ways in which you engage humans as some kind of sensor to collect information in a formal scientific way. So how do you take your pieces and components that you talk about in your application and structure them more to actually collect citizen science data?
Yeah, so I don't think we have.
Yeah, I think it involves
Yeah.
how personally defines
Right.
citizen science.
But we do have
Great comments.
a workshop, computing for citizen science. Are you involved with that?
Yeah.
Right. So we can discuss more in that workshop. Thank you.
Thank you very much. Thank you very much.
Can you put the mic in the center?
All right. So Na was an intern with us over the summer, and
Hi everyone, my name is Na Yang. I'm a third-year PhD student from University of Rochester. So my research area is wireless communication, and also during the summer I did a great intern job here at Microsoft Research about signal processing. So it combines with the mobile computing on Windows Phone 7. So the app I developed is called Listen and Feel. So that's an emotion sensor on the phone. Also, now we have Windows Phone 7.5, so we can also work on that platform. And my mentor at Microsoft Research is Ardman Samuel. Okay. So nowadays we have smartphones. They are equipped with a lot of sensors. For example, we can see the microphone, camera, and this is the accelerometer, which can detect the movement of your phone. And also we have the GPS, and also this one is the gyrometer, so it can detect the position. When you move the phone, it can detect the position relevant to the ground. So all these sensors enable a very convenient way we use our phone, and which also enables a lot of functions. And also, for some new concept, we can detect people's biometric information. For example, heart rate, blood pressure, body temperature, and skin sensation. For example, this concept phone from RIM is BlackBerry Empathy, which can detect all this biometric information from this little special ring. So that's external equipment. So we propose our notion. We have the physical condition can be detected from the phone, but how about our inner space? How about the people's emotion? So we want to propose this new emotion sensor on smartphone. The emotion is defined as a complex psychophysiological experience from an individual's state of mind as interacting with biomedical and environmental influences. So there are two main reasons why we want to put that on the phone, not on the server, on our laptop. The first one is that because people's emotion changes over time and space, so we want to do this emotion detection in a continuous way. So we want to have our emotion sensor on our phone, which is a company with us. And the second reason is that people may feel very uncomfortable, or they are resistant to report their emotion to a very strange device, but they may feel very comfortable to talking with their own device. So we hope that the phone can capture our real emotion. So here's the outline. First, I want to motivate the emotion sensor on some citizen science project. And also, we'll do a survey for existing emotion detection apps on other platforms. So we'll go detailed to the system architecture and how we deploy on the phone. And also, of course, we'll have the demo for the real app and some future work. So here's first, the citizen science project we propose is to measure the happiness index for a city or country. We have a very interesting video which will give you some concept about the happiness index we're looking to.
Of independence. But how do you measure happiness, especially on the scale of a community, a city, or even a nation? Well, in British Columbia, they're doing just that, measuring happiness, and not just for the fun of it. As Connect's producer John DeGraff shows us, it's part of a new global movement that considers happiness more important than money. Stratford effort isn't trying to make a fool of herself.
Does this encourage you to smile at a stranger?
I just did.
Yeah.
She works for the city of Victoria, British Columbia, and she wants people there to smile more for their health and contentment.
Do you think about your happiness?
Oh, yeah.
Yeah? And do you think that you're a happy person?
Yeah.
It's coming out of the work that we're doing as part of the Happiness Index initiative here in Greater Victoria. Part of our role in government is to have our citizens be happy and engaged in our community.
A lot of people in Victoria do, yes.
Yeah.
Happiness Index? But Kimberly isn't kidding. Victoria's been measuring the happiness of its residents for the past 2 years, and most of them seem pleased by the effort.
And welcome to Victoria.
We've had a little over 3,000 people take the survey.
Now some people are trying to make Seattle a happier city too.
I'm intrigued by it. I think we're going to learn a lot as a result of the project that's being undertaken to determine how people's levels of happiness is. And I intend to use that to help shape.
And for quite a while now, various organizations, including the Gallup poll, have been measuring happiness around the world.
The Scandinavian countries often come up on top. In those countries, there tends to be a pretty strong sense of community. There tends to be an economic safety net that makes people have less concern and worries about losing income and falling out of the economic system in ways that can be really harmful, generally lower levels of poverty. So those are the kinds of things that I think provide the framework and foundation for people to be satisfied or happy.
But researchers find that despite a half-century of income growth, levels of happiness in many wealthy countries, including the United States, are flat or falling.
And the mistake we've been making in the past is overestimating the extent to which money and GDP is going to contribute to our sense of well-being. That more money and more GDP is really all it takes to be happy.
So we can see that now officials are trying to propose policies that can produce more than just material well-being, but the sense of well-being for their citizens. There are largely two ways to measure the happiness. The first is to distribute some questionnaire or do a phone survey. So people will report their feeling. So that's kind of a subjective way to test people's happiness index. But we're thinking that maybe there's a more objective way. We can use the phone to detect people's emotion, not just to let the people to report their blissful feeling. So there are also, besides measuring the happiness index, we can also study some factors which can influence people's emotion. For example, time, place, and people. For this citizen science project, we have a notion that, in general, this kind of crowd-powered research can be greatly facilitated by the smartphones. So by crowd-empowered, which means this project are participated by so many people, so we can all contribute our effort to enable some great things. Another project I motivated is to use the emotion sensor on some social networks. For example, we can, like a photo, video, or a friend's status using our voice. For example, you can say to your computer or your phone, "You look so beautiful." Then it shows a like. So probably it would be great to have this label, like using listen and feel. And also, why we want to put that to for the social study is because that the social media is very popular nowadays, not just for people they want to post their feelings online, but also for some researchers in the psychology or sociology. So one researcher posted their results based on Facebook. So they do a data mining for the words. So we can see they got the people's gross happiness index from words, not just from emotion. So the keywords which denote happy, for example, happy birthday or happy Halloween, or some other this kind of positive words versus some negative words which present the sad emotion. So they are very interesting. We can see they are the people's emotion, so positive or negative. So you can see there are some sparks for those national holidays, which is great. But we can integrate that also with emotion, not just from words. Another project is in the healthcare field. So we want to take care of those patients with mental illness. For example, they may be unwilling to report the thing that trouble them. So we want the mental health counselors to effectively know their emotion, so they can react faster when they detect dramatic emotion change reported by the sensor. Of course, there are some other use cases, like in the role-playing games. I think game players, enthusiasts, they may be very inspired by this app. For example, they can influence the character's emotion by themselves, so which will enable very enjoyable user interface interaction experience. Also, we are thinking that maybe we can combine them with the Kinect sensor, or nowadays we have the Windows Tell Me, that app on Windows phones, so it can know your emotion when it's talking with you. Also, we can customize your phone. For example, if your phone knows that you are not very happy today, probably it can change the setting automatically or the background music. So all this effort, we're trying to build a more personalized and a lovely gadget about your phone. Okay. So there are already some emotion sense applications out there in the academia field or in the market. For example, the Symbian phone that the Cambridge University developed is called Emotion Sense, which can detect around 70% the accuracy based on 5 broad emotion categories. But our research is based on a totally different algorithms that I will explain later. And also for some very mature platforms, we have, for example, the Kinect from Microsoft Research, which can accept some verbal comment, but not emotions right now. For Android and the iPhone market, there are already some apps which developed by other developers, but none of them are intended to be contribute to the citizen science project, which we would like to do. And for the BlackBerry Sympathy, we have talked about previously, and the Symbian's phone, which can detect people's emotion not based on your voice, but based on the gestures or the facial expressions. Oh, sorry, the facial expression from the mode meter developed from researcher and the student from MIT. So let's move on to the architecture for our system. So our phone tries to detect people's emotion based on how you speak to the phone, not just what you speak. Not what you speak, but only how you speak. So it tries to extract some speech features here. Extract some speech features, for example, energy, pitch, or format, which consists of your phone, of your speech. And also, we can see when we capture users' voice, we do all this speech signal processing on the server. So this is all done by the server. And then we input them to a training system. So the speaker's sample is used as the test data. But offline, we can do something on the server too. Well, we have a processing database which contains all the speeches with different emotions, which performed by actors or actresses. And we'll show you what's actually in that database. So we extract this very huge database, also do the same speech signal extraction feature extraction. And then we have the training data here. And the machine learning algorithm we use is called logistic regression. So we can get the weight for those features. And then when we process the whole data, the test data, use the weight, and go through the learning system, so we can have the predicted emotion. So the server will give the feedback to our phone. So we'll show what the database is, how we do the emotion, how we do the speech signal feature extraction, and also how we train the system. But before we do that, there are two ways we want to think about. We can do all the computation on the server. That's exactly what we did. And then just to get the feedback from the server. So we have the advantage of, we have fast computation speed on the server, which is a very powerful machine. And on the other side, on our phone, we can consume less power, which can save our battery. But the problem is that because we need to upload the whole audio file to the server, so we have a slow data transmission problem. The other way to do this is to do all the computation both on the server and the phone. So on the other side, we might experience low computation speed, higher power consumption on the phone, but we have a faster data transmission. So let's talk something about emotion. So we can see there are all these emotions here is the happy emotion categories, and the emotions here are the sad emotion categories in a broader concept. This is from literature, but we add a pride emotion here and the shame emotion here, because in our database we have 4 emotions for sad and 4 emotions for happy. So we just fill up the position on the 4 quadrants. So the 4 quadrants is we can categorize emotion by active versus passive. For example, happy is very active, or angry is active, and the bored or content is passive emotion, not that severe. On the other direction, the positive emotion, for example, happy, and negative emotion, for example, sad. So here's our database. In order to get a very fair emotion, how to say that? We don't want to show that we detect emotion based on the words we say, but we want to show it's based on the how we say that, our intonation, for example. So what we say in this database is all very neutral meaning concept. For example, numbers and date. And we capture the voice from both male speakers and female speakers. These are the happy emotions, and these are the sad emotions. For example, we can play one. The pride.
June 20th. June 20th. October 5th. October 5th. 508. 508.
So you can see they are just the numbers and dates. Or we can play the sadness, for example.
August 2nd. June 28th.
Feel the difference.
June 28th.
Okay. Yeah. So I will show you how to do those speech signal feature extraction. There are something signal processing techniques. So the features we want to extract from the audio are listed here, like the pitch frequency, derivative of pitch frequency, and also frequencies of first 4 format and bandwidth of first 4 format. I'll talk about later what format means. And also in the energy domain, we have energy and the derivative energy. The reason why we introduce derivative of pitch and derivative energy is that the change of our voice can also say something. For example, if people are very excited, you can have a various change in our voice. So this one we can see this shows the waveform of our, like there are 6 utterances separated by the space here. So if the amplitude of the sample is greater than a threshold, we'll mark it as 1. So you have the second subfigure shows the sample marker. So this one is the frame marker, which after a smooth of the sample marker. So first we have a very noisy data because when we capture from the phone, we have a noisy background. So we want to do some pre-processing before we extract the features. So after apply a bandpass filter, we can have a smoother data to process. Okay, so this is the definition of pitch. So pitch is the relative highest or lowest of tones as perceived by the ear. It depends on the number of variations per second produced by the vocal cords. So the pitch extraction algorithm we use is the autocorrelation in the time domain. So we can see this is the waveform, this is the sample marker. So we can compute the compute the pitch for that audio file. And the second feature is energy. Also, we can compute the energy is shown here. So the formula is just the summation of all the square value of each sample, the amplitude of the sample. The third feature is format. So format is extracted from the vocal tract renaissance, determined by the shape of the voice tract. So it actually means where you generate the voice, whether it's whether your mouth is open or closed, or you speak the words in the front or on the back of your mouth, the position. And some researchers have studied that format bandwidth during slackened articulated speech is gradual, but during improved articulated speech is narrow. So that can show that the format can influence the emotion. So we'll show how to extract the format. So it's basically from the observed spectral envelope. Let's see this figure. So this shows we generated some airstream from our lung. We have the pulses here, and when the airstream go through the vibrating vocal fold, which act like a oscillator, so we shape them like this. Then when we output this, the output signal may look like this, which so we can see there are different frequencies, which is generated by the vocal tract, which act like the resonator. But when we detect the format, we do the other way around. What we have is a waveform, and we can do the Fourier transform to get a spectrum. But we don't know the shape of the gain, the shape of the gain. So we use the linear predictive coding to do the signal processing to extract the gain. Okay, so let's summarize all the features we want to extract. So when we have all these features, we want to input them to a training model. So the algorithm we use is called logistic regression, which is a very simple machine learning algorithm. So the principle is that we create this formula with the input, and then we can see the output will look like a regression curve in a relationship with the input. And the input is consists of different risk factors. So the risk factors here are the speech features we just extract previously. And then we weigh them with beta, which means the regression coefficient. Then we get the input. And then after apply the input to the logistic regression curve, we get a value. So we can set a threshold, for example, if above 0.5, which will give us a happy emotion. On the other hand, we'll get a sad emotion, which is very simple. So here are some results. We can see that the pitch value and the energy value influence the outcome a lot because they have a large weight to the emotion detection outcome. And by doing a cross-validation test on the database, we get a 71% accuracy. So the precision is calculated by the correctly predicted good emotion and bad emotion, and divided it by the total number of samples in the database. Okay, so before I show the demo, I'll say how we deploy everything together. So as I talked before, I have the speech signal processing is done by MATLAB, and also we implement the machine learning algorithm in C#, and also design the phone app interface and do the test. The emotion detection service is deployed on a server on Microsoft Research. So we use the Internet Information Services to hold the service. To do the server and phone communication, we need the Windows Communication Foundation. So all these components enable the success of our app. But also we may have, when we do the test, we may have issues like configuration to configure the firewall, proxy, Internet Information Service, and also some access control problem may occur. So all this will make the success of our app working. Okay, here's the demo time. On the phone, we have it's developed actually from the app of a microphone application. Beside these three buttons, the record, play, and stop, we add a new button called Feel with a little heart shape. So it can, when we press that, it will upload the audio file to the server and do the emotion detection. So this is our application. So when we go into the application, we can press the tape shape button to record our voice. We can press this to stop recording. And then when we have the voice, we can play it back, or we can just send it directly to the server. And then we'll wait for some time for the server to react, and then we'll get a feedback here. For example, it says, you have a good mood, which means happy. So here's a video that I would like to show.
So we can see we have the bottom bar here. The recording button, play.
Oh, excuse me.
So we can see we have the bottom bar here with the recording button, play button, stop button, and the feel button with a little heart shape. So first, let's try something happy. Hey, the app is working now. Press the feel button. So the whole audio file will be sent to the server. The server will do the computation to try to detect the emotion. Okay, now we receive the feedback. It detects the happy emotion. Okay, so let's try something different. In Rochester, for example, we're approaching the end of the snow season, but somehow there's a snow shower again, so people may say, oh no, it snows again. Press stop. Then that detects the emotion.
There's some delay for the mouse.
Okay, it says, hey, are you not very happy today? Cool. That's exactly what we are thinking. Of course, you can, if you are expecting a snow shower, then you can say the same thing but with a different emotion. Hey, it snows again! Press stop and then the feel button. Let's try.
capture that.
Keep watching.
Okay. Of course, I have the phone here, so if you're interested, you can. So you can try the app out yourself. So for some future work, we can see there are 5 things that we also need to do. First, we want to test the precision because currently we just have the prediction result from the cross-validation simulation. So we want to test them on real users, and our aim is 300. So hopefully we can have this app deployed on several phones and then do a road test to get the prediction result. And also we want to compare the performance with other platforms, as I mentioned before, like Android or iPhone. Also with different background noise level, we want to see how much it will affect the precision. The second one, improve precision. We can, when I test the app in a preliminary test, there's a problem. It tends to detect happy motion for female and sad emotion for male. So I think this problem is generated by the pitch detection, because when we all know that female tends to have a higher pitch than male speakers. So and also a higher pitch somehow indicate happy. So we want to get the gender information first and then detect the pitch value. I hope that may help. Another way to improve the precision is to get to enlarge our training data, not just from the database, but also from the sample collected from the real users. We're expecting that with this, with more feedback, that can enhance the accuracy of our system. Third one is to refine the app. Currently, you can only support only one user using it at one time. So we want to support multiple users access the application simultaneously. Another point is that we want to study the trade-off for the 2 ways, like I mentioned before, whether we do all the computation on the server or we split the task on the server and on the phone. And also, besides happy and sadness, we want to support more emotion categories, for example, like angry. Also, this app now is only a standalone app, so we want to integrate that to a real citizen science project which can benefit the society. And after getting the data from real users, we can analyze the collected data. Maybe we'll have some new findings and some new ways to improve the accuracy. Also, because when we improve the app from a standalone application to a real application, we can help the citizen science project. We need to modify the app, which can detect people's emotion as a background, as an app running in the background. So there are some things need to be modified. Finally, we are thinking the other way around. When we have the ability to detect people's emotion, maybe we can color the conversation with different emotion. So like in the call center, we can color the speaker's voice with different emotion, so as if you are talking with a real person. That should be interesting. So here are all the references, and also I'd like to take any question you may have. That's my email address at Rochester. And finally, wish everybody have a happy journey to Sweden. Here's a quote by Mark Twain. Happiness is a Swedish sunset. It is there for all, but most of us do the other way and lose it. That's it. Thank you. Yes. Yeah, go ahead, Claudia.
I was a little bit puzzled by your claim that questionnaires are subjective and voice analysis is objective. Because voice analysis at the moment right?
Right.
And questionnaires could be long-term. And moreover, there's at least 50 years behind the questionnaire science.
Yeah.
Okay, so why do you say that? How do you justify this claim?
Yeah, maybe I shouldn't say that very, that confirm that questionnaire is subjective. But questionnaire is, you can report your, for example, satisfaction for the, your living standard in that city, like in Stockholm. So people can give some suggestions like how to build a better city. But the emotion that we're trying to is kind of a short-term emotion that you want to detect your current emotion. For example, at the application I proposed, like to modify the monitor the emotion for some patient with mental problems, so their emotion maybe change dramatically. Yeah, I think both ways will help. We can combine them together. Yeah, thanks for your question.
Yeah, nice work. But I'm curious to know what your thoughts are on, how this works with different speech contexts. So, for instance, some languages, they always sound as if you're angry.
Yeah, for example, like German, it may sound very strong emotion.
Or, I might be a person speaking a language like English, but
yeah. Yeah, we also have some thought on this. So we're thinking that maybe we can customize the accuracy for our own phone using our own voice, so it will know what your emotion, the standard level will be. So.
Yeah, come with the app. It's like those people, female and male, kind of distinguished. There is a calibration that needs to be done according to the cultural backgrounds, whether or not you're speaking your native language, all that kind of attributes contributes to the calibration system.
Yeah. So first we can let your phone get used to your voice.
Right.
Yeah. So yeah, that will be a nice future work. Thank you.
Questions?
Yes.
How much learning requires to adopt a new person? Maybe is it? Is one instance of application is it meant for only one person, or it can also? It can also detect the emotion of maybe some other person.
Yeah.
Secondly, as you said, in medical science, maybe it is useful so that a psychiatrist can continuously monitor his patient. But most people will not have such problems. How it is useful for me to rely on my mobile to detect my emotions other than myself. I can detect my inner state of mind more better than that.
So your question is your first question. Yeah, your first question is whether this app will work for a broader population, not just for one person. Yeah, and second one is how to use that in political science.
You said that in medical science it may be useful for a doctor to
monitor a patient. Yeah.
But how it is useful for common person, maybe a mobile user, to find his state of mind other than myself? I can also detect what's my inner feeling.
Yeah. So yeah, there's a very important notion that a normal person can detect the people's for example, another person's emotion very quickly, but we want to do that automatically. So that for your second question, I hope that can answer your second question. We don't want to ourselves to determine our emotion. We want a third party to automatically detect our emotion, which can get some report.
Also related to the learning process that you have, because learning, it seems to me that if, for example, you are using some kind of neural networks, then it adopts to some training data. Then if I am trying to detect the emotion of some other person, then it is not trained for that person.
Yeah, maybe that can combine with your first question. So currently we are doing on a broad database. So there are 5 speakers, both male and female. So maybe we can use a larger database if we can cooperate with some companies like Microsoft Research, so we can get access to those huge database. Hope that can will be helpful to shape our app to a better one.
Yeah,
okay. Yeah.
We can take the discussion over to the lunch. So thank you again.